Hello, my name is Dustin Scriven. Today I'd like to talk about the development of position and neutron gamma discriminant neutron detector modules that we've been developing at Texas A&M. So our project is motivated by the need for more modern high-resolution neutron detection systems with both good spatial and temporal resolution. Such devices have a plethora of applications such as fundamental research, neutron spectroscopy, neutron correlations, as well as national security applications like portal monitoring. The active detection material used in our development project is an organic scintillator called paraterphenol. Paraterphenol is very bright when compared with other modern organic plastics, and it's also a very fast scintillator, and it has excellent neutron gamma pulse shape discrimination properties. The first step we took was to explore the effect that spatial resolution had on the energy resolution, and we did this using JANT4, simulating neutron time of flight measurements from a large array of paraterphenol. With smaller and smaller crystal sizes, we found diminishing returns, and when compared with the cost analysis, we settled on 2 centimeter crystals. Our largest development was finding that by optically coupling the individual 2 centimeter crystals together into what we call a pseudobar, a discrete spectrum was generated when looking at events with left and right sided coincidences. During development, a single bar was exposed to californium 252 for its continuous spectrum of both gammas and neutrons. With that, we found that the discrete nature of the position spectrum was actually energy dependent. We employ a standard figure of merit that's typically used for neutron gamma discrimination to describe the position separation and to identify a threshold. The figure of merit is extracted at interval cuts 50 keV EE wide, and a threshold was defined where the figure of merit equals 1. In the case of the position, we found a position threshold to be 300 keV EE. By looking at events from each of the independent crystals, we then look at the neutron gamma pulse shape discrimination. And with a similar figure of merit treatment, we find a PSD threshold of 150 keV EE in all crystals. Lastly, we looked at the timing resolution by observing coincident 511 keV gamma rays from a sodium-22 source. With a cesium fluoride detector as a start trigger and each PMT of the pseudobar being a stop, we're able to measure the timing resolution for each crystal as seen from the left or the right PMT. Using weighted averages between the left and the right, we extract a time resolution not worse than 700 picoseconds for every crystal in the detector. To conclude, we found a method for producing position-sensitive neutron detector modules with position and PSD thresholds of 300 and 150 keV EE, with timing resolution better than about 700 picoseconds. These results are currently under review with NIM-A, and a construction of an array using these modules is underway at Texas A&M. And lastly, this work was funded by the DOE NNSA Centaur grant for low energy nuclear science. And I wanted to say thank you to my collaborators at Texas A&M and at Washington University in St. Louis. Thanks.